June 20, day 6 or 7. I don't know. I can't see anymore. I have no idea. But back once again, 2 problems due today. Probably gonna do some random ones after that. But we shall see. We're in a different beanie today. Kind of pog, kind of different, kind of exciting actually. I forgot what I was gonna say, but just finished recording a video on a different channel, and excited about that. There was a comment on a different video by the Control-C Ninja that I wanted to address. Great comment, by the way. Even better human, by the way. But the comment said spaced repetition for LeetCode problems. I think spaced repetition for LeetCode problems and spaced repetition to our spaced repetition. Usually spaced repetition is for flashcards, for something like atomized pieces of information. But I try to use spaced repetition for a bunch of different things, and really using spaced repetition with problem solving as a vehicle to encode basic information, I think is pretty cool, just because by the process of like logisticizing something, if that's a word, I think helps really understand it. And I think part of the process for me is pretending like I'm teaching the problems. So, you know, I think there's a version of it called the Feynman method, but I think even anecdotally, I think we all have the experience where like maybe someone asks you to teach someone something or show someone else how to do a problem, and just like the mere act of showing that person how to do it automatically, or like it's kind of like the sledgehammer, and forces you to make sense of it yourself. Because if it doesn't make sense to yourself, then you can't articulate the words. And so I think the problem solving and explaining it like I'm teaching it every time helps me understand it, which is pretty cool. So if you're considering using spaced repetition for problem solving, I would highly recommend it. But let me slow down. And if I'm bumping up, jumping up, running, if I'm bouncing up and down, I'm kind of shifting left and right, it's because I'm walking. Gotta get my calories in because my heart's gonna fail. But I'm gonna jump into it. Climbing stairs, linear time, linear space. Oops, almost forgot my countdown. So they have a function, climb stairs, which takes a number and returns a number. If you're climbing a staircase, it takes n steps to reach the top. Climbing a staircase takes n steps to reach the top. Each time you can either climb 1 or 2 steps, and how many distinct ways can you climb to the top? So n equals 2, there are 2 steps you can take to reach to the top, starting at the 0th step. How many different ways can you take to the top? So n equals 2, the output is 2, you can take 1, 1, or you can take 2 steps. So there are 2 ways to climb to the top. N equals 3, there are 3 ways to climb to the top, 1 plus 1 plus 1, 1, 2, or 2, 1. So I think what we're seeing here is that order matters. So 1, 2, and 2, 1 count as 2 different ways. And n is never greater than 45. So this screams recursion to me, because usually the numbers 1 or 2 scream recursion. And so how could we go about solving this in a way that makes sense? So I think we can use recursion for this, and then use a memo array to memoize the problem so that it is, so we don't end up recalculating portions of the tree over and over and again. So why does this problem have a tree-like nature? I think it's because of the branching, right? If we have node 0 here with this, you can imagine this as a binary tree, right? You take 1 or 2 steps, so there's a branch. You take 1 step here and 2 step here, right? With the 2 step here on the right, you already reached where you want to go, right? So that would count as one valid way. But at the 1 step here, you're going to have another branch again, where you take another step and 2 steps. So at each step, we're going to call this recursive function and ask, hey, if we take if we take 2 options from here, 1 or 2 steps, can we get to our goal number, which is 2? Well, we can by doing 1, 1, and by doing 0 and starting at step 0 and taking 2 steps. Once we're at step 1 and we take 2 steps, we go past step n. That's a negative outcome, right? So we have to handle that. So there's probably 2 approaches to this, where you could start at 0 and go to n, or you could start at n and go to 0. I think bottom-up approach here is more intuitive, and at the same time matches more nicely in my head with the whole climbing stairs analogy. So we could define a function that we're just going to call helper. And why do we want to call this function helper? It's mostly just because I really don't know what the function should be called. Calling it helper simplifies the process. We're going to want to pass in 2 parameters. One is going to be where we're starting at, which is 0. It's going to be the node that kicks off the decision process. And we want to know when to stop, right? That's going to be n. We also want to pass in a map, and this map is just going to help us to optimize the problem in terms of pruning the recursion tree. But I don't think we'll use it in the beginning, just for the sake of learning. But we have the I call it climb. We can call it helper, and then we'll call it pos, which is going to be a number, and which is going to be a number, and a map, which is just going to be, you know, a map of type number, where both the keys and the values are going to be numbers, and we're going to return a number. Right, so what can we do here? We said at each position we have 2 options. You can take 1 step, or we can take 2 steps, right? But we can't jump into that yet, right? We can only take 1 step or 2 steps if we haven't passed our goal step, right? So if we're at step 4, step 3 in this case, right? We don't want to, there's no point in checking if we can take 1 or 2 steps, because our goal step was n equals 2. If we're at step 3, we already messed up. What does that mean? It means we want to handle the case where we pass the step, right? So if pos is greater than n, well, we want to return 0, right? Because it's not a valid way to get the number of steps. If we ever reach pos, right, then we want to return 1, or some way of counting it, because we want to persist that value. But if we're greater than n, we don't want to, right? So let's go to a different case. Let's say we're at case equals 1, right? We're not at n yet, right? So what do? Well, we want to calculate, actually let's do it without map first, but we want to calculate how many different ways we could get to 2 from 1. And so what does that entail? Well, I think we just have to enforce that decision process of taking 1 or 2 steps. And I think we could call this helper function, which is going to, in the middle step, right? So if we want to have one more, if pos equals n, then we found a valid way to get to the second step from wherever we were before. Right? We don't really know, right? Our previous step could have been 0, it could have been 1. All we know is that we made it to 2. So we can return 1 here, and then, right, we handled our case where we pass our goal step. We handled the case where we reach our goal step. What's the missing case? Our missing case is when neither of those are true, which means we're trying to get to our goal step. So how do we recurse this? Well, we would say, hey, take 1 step from where we are, go to end, and we're going to pass in the map, but also add it to where we are right now, but take 2 steps, and just follow that through and see what we end up with. So what we end up with is this really, really long addition expression, right? It could be something like 0 plus 0 plus 2 plus 1 plus 0 plus 0, right? And basically it's just to illustrate that the way we're getting this answer is really just by stringing together this really long operation of taking 1 step from where we are, falling into one of these 2 cases and returning 0 or 1, and then stringing it together as addition. So, well, I think this works. I think a good thing to do is run it in our head. So let's pretend we have n equals 2. and we're going to start at 0, go to n, we're going to pass in the map. So we're at 0, pos is greater than n. Well, 0 is not greater than 2, right? 0 does not equal 2. So what are we going to do? We're going to turn the helper of pos plus 1, which is 1, and pos plus 2, right, which is 2. So now we're going to be at, so I started at 0, right? Now I is, and a good way to visualize this would be like this, right? So we said we're going to return helper pos plus 1 of end and pos plus 2. So now we have something plus something, right? So we can run that in our head. We have to run helper for 1 and helper for 2. So what does helper for 1 equal? Well, now at index, or at the number 1, right, how do we calculate our value? Where our pos is 1, right? Is 1 greater than 2? It's not. Does 1 equal 2? It's not. Right, so we're going to return the helper of pos plus 1. So 1 equals the h of pos plus 1, which is 2, which equals something, plus the pos plus 2, and our pos is 1, so 1 plus 2 is 3, so we have the h of 3 equals this, right? So, let's keep going. Well, we have to do the pos plus 1 first, and actually it would have been a little more easier to understand if we did it like this first. So I'm going to delete some of these lines just to follow the recursive chain. So now we're going to be at pos plus 2, right? Pos equals 2, right? And so let's see what we do. Well, is 2 greater than 2? No. Does 2 equal 2? Yes. So we actually return 1, right? So h of 2 equals 1. Well, we actually had to do h of pos plus 2 going to n, so now we have the second half that we want to handle. So do h of pos, which is 1, plus 2. That's going to be h of 3, which equals what? Well, let's check the function. Is 3 greater than 2? It is. H of 3 equals 0, right? So this return here is 1 plus 0, right? And that means that h of 1 is actually equal to 1. Yeah, it's actually equal to 1. We have the secondary recursion call that this function that we have to call, right? And that's going to be the h of 2, right? And we can see that we already did h of 2 before in the past, but we're actually going to recalculate it anyway. So h of 2, is 2 greater than 2? No. Is 2 equal to 2? Yes, we return 1. So we end up returning 1 plus 1, right? And that returns 2, which gets us the correct answer. So there's two things we see here. The first thing is that the way we've structured this works. The second thing that we're noticing is that we're actually going to duplicate a lot of calculations. We're only going from step 0 to step 2 here, but if we actually go from step 0 to like 45 or something ridiculous, we would actually be recalculating a ton of nodes, even though we've already calculated them. And this is where this map comes in, right? If we can already save the value, then we want to save it, right? And that is the secret sauce to making this work. And I'm just gonna run this. It's not gonna work completely for all the test cases, but it should work without the map for the first case, just to show that our logic works. And so this is good. And so then we want to use this map. I actually just redeclared it, and I passed into the function ahead of time. What we're going to do is just going to say value equals helper. And then what we're going to do is going to say, now that we know, we want to save all the values we can, right? So we have map.set, and actually I'm going to undo this just because I want to keep the original thing we already recursed through. I'm going to say const value equals helper. So now we're just going to keep the value first, and then we're going to set it in the map, right? So map is a key value pair, but what's going to be our key? It's going to be the position, right? So whenever we call for the function, if we do h sub 2, for example, right? Or let's do a better one, h sub 1. it's not greater than 2 and it doesn't equal 2, right? So what do? We calculate its value. We already know that the h of 1 is equal to 1. So it actually ends up getting filled into the map is for key 1, we get the value 1. We know from step 1 there's one way to get to 2, right? And so that's what we want to do, and then we can return map.get value for pos. But this actually isn't all the way there yet. The reason that is because now we're just saving the values in the map. We still have to use them, right? And so one thing we can do is we can say if, make this else if chain longer, if map.has pos, right, then return map.get pos, right? And so this is going to allow us to save all recalculations. So if we were to recurse through this again, right, as we did originally, once we get to 2, right, we return 1, right? And since we returned 1, we go back to h sub 2 and we'd say, well, the helper for index 1, we know that from index 1 we can get to index, we know that from step 1 we can get to step 2 by taking one step, and so we can save that in the map, right? And then once we get back to h of 2, well, we can check, hey, do we already know how to get to step 2 for this position 2? And we'll check the map. Well, it does exist in the map, so we'd return 1, and this allows us to prune the recursion tree almost to linear time, basically, because once we visit a node, we know how to calculate the value for it. We already know the value for it, right? And so I think this should work if the map, if it exists in the map, then we get the value of the map. Otherwise, possibly return 0, possibly return 1. Might also be wondering, why don't we have to save this value, right, and save it into the map? It's because this function is ultimately called as a function of the same function, right? So when we do helper of pos1, we take one step, right? It's not important that we know that at step 2 it's not important that we know that we got to step 2 and save it in the map, right? So if we did, for example, set value equal to 0 for these, this is actually unimportant, because when this equals 0 or 1 is when we've passed it, or when it equals 1. So what we're setting for the map is actually all the values we don't need, right? We know that once we get to 2, we got to 2, and if we're saving the values for the other ones, it lets us prune the recursion tree as well, but it actually is more crucial that these right here, this right here saves it to the map. Now, I'm a little skeptical of this function for some reason, but run it. I actually should have run it in my head before. Oh, okay. But this is the real test. Does it prune the recursion tree? And it looks like it does. There's something I wanted to try here. So what we're doing right now is we're declaring a function map. We're declaring a function map. And we're passing in, and we're declaring a helper function when we're passing in map. But I'm wondering if we can streamline this. And this looks a little bit nutty. And I actually don't know if this is good or bad practice. But I think we can turn this into a closure and shrink the code just a bit. But it actually makes it harder to read, so it's probably not a plus. I actually don't know the type syntax for declaring a closure. It always gets me. I mean, like with TypeScript at least. If you return the function, I guess, yeah, I think this is fine because we're closing over the values here. Or maybe this looks completely nutty. We actually don't have to pass this into the function anymore because we're closing over it, which means we should already have access to the map. And we call it, we don't need ideally you'd return this as a function and then call climb stairs. But I wanted to see if I could do it in the function they're going to call, which is, maybe there's no point in doing that. I actually don't know. Let's see. Okay, so you still get the expected output. So, you know what? Maybe this is fine. Maybe that's fine. Maybe that's an improvement. Maybe it's not. Who knows? But that is climb stairs. That one took me a little longer than usual. But I really wanted to work through it in my head to make sure that I understood it. Time complexity is 2 to the n, right, without pruning the recursion tree. Space complexity would be linear space. Depth of the recursion tree can go up to n. This seems to be a recurring thing for recursive problems. The worst case scenario seems to be linear time, where the number of calls is bounded by the height of the tree. So for n equals 5, we have 1, 2, 3, 4, 5. So for some reason, recursive functions, or not recursive functions, but recursive problems that revolve around binary trees always have to deal with being bounded by the height of the tree. And that's something to keep in mind, I guess. Maybe next time we'll try with the array. Confirm. Missing number. So we have a function missing number, which is an array of numbers, and then we have number. So we have an array of numbers, we have to return a number. Given an array containing n distinct numbers in the range 0 through n inclusive, return the only number in the range that is missing. So if you have a range of numbers and they're all distinct, going from 0 to n inclusive, which is distinctly different from a for loop, which is exclusive of the end, then they want us to return the number that's missing. One way to do this would be to sum up all the numbers in the array and then sum up the expected value for all the numbers in the range, because the numbers in the range are 0 through n inclusive. So we know what the sum should be. It should be the sum of the series of going from 0 to n. But we don't know what that is for nums. So if we sum them both and we take the absolute value of the difference, that should give us the missing number. So we have 0, 3, and 1, and we can see that the missing value here is 2. Looking from the array, it's hard to tell that there's a value missing, I guess, without knowing the contents. But it seems to be that if you have 3 numbers, or if the array has 3 numbers in it, then you know you're missing a number because the array should have 4 numbers in it. Because, for example, if you look, I guess it's because the range of 0 through n inclusive, so 0 might be missing. If we have a range of 0 through 45, there should be 46 elements in the array because of 0. It shows that the arrays are not sorted. The number of elements can be up to 10 to the 4. I actually don't know what that means or how high that is. The numbers can be 0 through n. All the nums and nums are unique. So I think you could just sum these up. So you could sum nums up with a reduce function. We'd have a and b, and we return a plus b, right? But then you need the sum of the series, and you could write a for loop for this, but you can also do this with Gauss's formula, and that allows you to calculate the sum of a series in constant time. And we can just do this by saying nums.length times nums.length plus 1, and wrapping it over 2. And then we can return the math.value of the difference to get the distance between the numbers, which would be the missing number. So Gauss's formula is n times n plus 1 over 2, and that looks good. N times n plus 1 over 2 using a reduce function to calculate the sum of the number in the array. So Gauss's formula isn't that much of an improvement. It just allows us to save calculating over the range, which would have been 2n. But we drop constants in bigger notation anyway, so we're not saving that much time because you still have to calculate the sum of the actual numbers in the array, which takes linear time, which is just 1n. So pretty much the same, and I think this should work. So that looks good. Linear time, constant space. Past that, and you know, I'll do a random one. Symmetric tree. This is going to be one that takes it into mastery. So we have a definition for a binary tree node. We have val left and right. These are all properties on the class. Standard for a binary tree node, or just a tree node. We have a constructor that simplifies the way we set up values in it. We have function is symmetric, which takes a root, tree node, or null, and returns a Boolean. Given the root of a binary tree, which would be 1 here, this is the root, check whether it is a mirror of itself, symmetric around its center. So checking whether it is a mirror of itself is kind of like folding it on top of itself. So we're not really going to want to do a pairwise comparison. So you wouldn't want to compare 3 and 4 and 4 and 3. You'd want to compare both nodes on the outside together. So 2 and 3, 2 and 3, and 2 and 4 and 2 and 4. Right, and so this would be false because if you fold it over itself, it would not actually be a mirror of itself. We need 3 to go over here, or this 3 to go to the left subtree. We can have approximately 1,000 nodes in the tree. Could you solve it both recursively and iteratively? I think we can do it recursively, but iteratively gave us a challenge last time. So for example, if we have this function is symmetric, usually when we do a recursive function, we only pass in, or we recurse over a binary tree, we usually only pass in one node, or we're returning a node. Well, this one's a little different because we're going to be working with subtrees. So the 2 parameters that we're going to need are actually going to be root.left and root.right. And then one thing we'll check is if root, or if not root, then we'll just return. If it's empty, is that symmetric? We'll assume true because the problem doesn't say so. Then we'll return function helper, which takes the left node, which is a tree node, and or null, and right node, which is a tree node, or null, and it returns a Boolean. And so this is actually similar to the problem we did with climbing stairs, where we're at the end of the whole problem. What we're really doing is stringing together a long sub-expression of addition of 0 plus 0 plus 1 plus 1 plus 0 plus 0 plus 1. We string these all together, and that is actually our answer. We're going to change it for this one, and what we're actually going to do is symmetry, right? So we're going to just imagine the variable or 0 or 1, right? I'm just going to duplicate this like the other problem. Imagine 0 or 1 here not as numerical values, but as Boolean values. So 0 is going to indicate a falsehood of symmetry, 1 being a symmetry, 1 indicating symmetry. And so that's a very similar intuition for the problem. And instead of pluses, we're just going to use a bunch of ands, right? And the only way this works, right, is if the entire sequence of ands is separated by 1s, right? So if we have a tree that looks like this, our output is strung together at the end as a sequence of expressions of and 0, and 1, and 0, and 1. It's already false. The tree is not symmetric because we're looking for the golden case, which is going to be symmetry. It's going to be mirrored. All the nodes will be mirrored. We would return n1, 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 n1. That would be true. So how do we go about creating that environment? Well, the first thing we have to do is make sure that we're handling the cases that we can handle before we actually get to calculating anything. And what I mean by that is we can't check if 2 subtrees are mirrors of each other if they don't exist. So if left equals null and right equals null, right? That's technically a positive outcome because they both don't exist. And that technically means that we're symmetrical there. So we can return true. Another else if is if left equals null or right equals null. Here we want to return false. And this seems a little counterintuitive because these are the same conditions separated by ands and ors. Well, up top we're saying if we're both don't exist, that's symmetry, right? And if we get past this point, we know that at least one of them exists, right? So if we get to this second if and we realize that, hey, one of you is equal to null, we're already asymmetric. So we want to return false there. The false there would be indicative of a 0, right? If we get past this point, it means that we're sort of good. We know that both nodes exist, so we can continue with the sub-expression chaining. So here's where we start to chain the expression together. It looks a lot like climbing stairs. We're going to return, and this is, we're going to rewrite this line in like 5 seconds, but it's just for the sake of falling into traps on purpose. We're going to want to do the symmetry of left. So how do we call for symmetry here? We're in the function, the recursive function. You know, we're in the subtrees of left and right. So left and right, if we have the root right here, and we're passing into our function root.left and root.right, it means if we're in this helper function, we have access to this 2, which is the tree of the left subtree of root, and this 2, which is the root of the right subtree. So how do we check that these two are foldable over each other? Well, the first thing, right, that we can check, if their values aren't the same, there's not even a point to checking their children, right? What do I mean by that is if we have another tree where we have 1 here, 2, and 3, there's no point in checking these sub-trees because the numbers in the nodes themselves don't match. So there's no point, right? So how does that work? We'll just say if left.val equals right.val, that's awesome. And because of how short circuiting works, this is going to save us a couple of calls. They are the same value, right? So how do we know if they're the same value? That's good. We've pre-validated the minimum conditions to recurse again. So what do? Do we call helper once? Do we call it twice? If we call them once or twice, what nodes do we even use to pass in? So if we pull this image out of the screen and fold it on top of itself, what does that look like? What it looks like is we have access to the subtrees. We want to make sure that 3, 4, and 4, 3 match. Well, would we compare 3 and 4 in these two nodes right here, or 4 and 3? We compare neither, right? What we want to compare is left subtree, which is 2, dot right, and right dot left. And we want to compare left dot left with right dot left. So they're kind of like slightly the inverse of each other. And we want to do this by calling helper twice. And so we want to check, like we said, left dot left. Helper always takes two two subtrees to compare against, right? And we want to do this with helper dot left. So left dot left, and compare it to right dot right. And we want to call helper again and compare it with left dot right. So 2, 4, and right dot left. And if all of this pans out, this long sequence of 0 and 1 and 1 and 0, then we should be good. And just to gain the intuition, we can run it in our heads real quick. If we're given this root tree node, let's run this in our head. So the root node isn't empty. We know it's not empty because we can see all the nodes exist here. We're going to call helper root.left with root.right. Okay, so what does that look like? Right now, L equals 2, R equals 2, right? And we're returning this, right? This equals H sub r, which is technically 1. So let's just do it like this, how we did last time. If we do the helper function of the root, right, what does that look like? What do we end up doing? Well, both nodes aren't null, so we're not going to return anything here. Well, is at least one of them null? Well, neither of them are null, so we keep going. Well, we want to return the left.val if left.val equals right.val. Well, let's check. Does 2 equal 2? We're checking, and it looks good. We're going to ampersand that with helper left.left and right.right. So left.left is 3, and right.right is 3. Right? So that means we're at nodes 3 and 3. So now we're in the function again with 3 for left and 3 for right. Well, are either of them null? Nope. Are both of them null? Nope. So now you have to ampersand again. Well, okay. So now you want to return, if we do the h sub three and 3, h sub 3 and 3 equals, well, does 3 equal 3? It does. And then we're going to ampersand that with helper.left and left, right? But that's null. And helper right.right. Well, that's the right-hand side of this node right here. Well, that's going to be the h of null and null. Well, what does the h of null and null equal? Well, if we look at it, if both are null, then we return true. So that actually returns true. So h of null sub null is technically true. Right? So then we go back up here, right? And we're at 3, 3, right? And there's one more to do. So left dot right and right dot left. So these two imaginary nodes right here. And we know that both those are null. H of null sub null is true. All right, so we go back up to the root where we originally were, and we know that h sub 3 technically equals true. And so we're going to do the second half now for the node. Well, we were at the root, which we called with 2 and 2. I should have made this makes more sense if we do h sub 2 instead of root, right? And so that is where I'll stop for now.